Okay, this is the set of solutions for the arc length problems. With the revision of the BC exam for 2020, not all of these problems are eligible. I'll point out which ones are. Definitely number one is you're given the function y is equal to the tangent of x. We're going to need the derivative of that function. So that is the secant squared of x. The arc length is always the integral over the given interval, a to b, of the square root of 1 plus the square of the derivative with respect to x. So this is in the one-dimensional case. As far as I can understand, the one-dimensional case will be the only case that is tested on the 2020 exam. So because they're knocking out polars, parametrics, and vector valued equations, so that's like that whole unit 9 is being dusted off. So the one-dimensional case is still in. This is the one-dimensional case. This is an arc length problem. Note that they gave you the restriction that a and b had to be between 0 and pi over 2, and that's causing us to not have to deal with an improper integral because the secant is not defined at, let's see, secant is 1 over cosine. So the problem with cosine sneaks in at pi over 2. So just being aware of that, and the tangent itself is not defined at 0, right, on that interval. So that's why they had to have that restriction in there. Anyway, the restriction between 0 and pi over 2 makes this a much more simple problem and allows this to be letter D. You just use the formula, throw it in there, and you're good to go. All right, so let's look at number 2 here. Number 2 is definitely in the mix. 2 requires a little bit of work here. You need to know, in order to do number 2, you need to know the derivative of the secant. Okay, so I'm going to throw that over here. I'm going to let z be the secant of x. I'm going to demonstrate that dz dx, let's see, that's 1 over the cosine, right? So I just applied the quotient rule here, low d high minus high d low over low squared yields sine of x over cosine squared of x. That's going to become 1 over cosine x times sine x over cosine x, which is the secant of x times the tangent of x. So that's one of those like deep cut derivatives that some of you may have memorized, but if you don't, there's the pathway to get to it if you're stuck on that on the test. All right, so we know that y is the natural log of the secant of x, which means dy dx is 1 over the secant of x times the secant of x times the tangent of x, because that's the derivative of the inside that we just found out over here. The secants cancel, which means the derivative of the natural log of the secant of x is just the tangent of x. Woohoo. All right. So that being said, I'm now ready to set up my integral. I have to go from 0 to b of the square root of 1 plus the tangent of x, and then we're going to square that dx. Okay, so this is one that we've seen before. 1 plus tangent squared of x comes out to be cosine squared x over cosine squared x plus sine squared x over cosine squared x, which is, well, cosine squared plus sine squared is 1 over the cosine squared x, which is the secant squared of x. Okay, so if you don't remember this from the surfer and spotter thing, 1 plus the tangent squared of x is equal to the secant squared of x. Those are interchangeable. So this is how we get to the integral from 0 to b of the square root of the secant squared of x dx, which is the integral from 0 to b of the secant of x dx, because on the domain restriction there from 0 to pi over 2, the secant is always positive, and I don't have to deal with the square root or the absolute value. So that one is A. All right, so there's a couple of weird turns in there, but just be aware that they exist. All right, there we go. All right, so let's look at problem number 3. Problem number 3 is pretty straightforward. We're given that, oops, isn't technology grand. All right, so we're given that y is equal to 2/3 x to the 3 halves. So dy dx is going to just be x to the 1/2. All right, so the arc length will be the integral from 0 to 3 of the square root of 1 plus x to the 1/2 squared dx. So this is the integral from 0 to 3 of the square root of 1 plus x dx. Now, in theory, I have to do a u substitution here. In reality, I don't, because the inside of that square root has something that has a derivative of 1. So when you do the u substitution here, du is just going to equal dx. So when I take the antiderivative here, I can really just say, okay, this is the integral from 0 to 3 of 1 plus x to the 1/2 dx. This is going to be the same as 2/3 times 1 plus x to the 3 halves, right, from 0 to 3. Give myself a little line here. That comes out as 2/3 times 4 to the 3 halves minus 2/3 times 1 to the 3 halves. So this, let's see, square root of 4 is 2, cubed is 8, so this is going to be 16/3, and minus 2/3 just gives me 14/3, and that's answer C. So there you go. That's number 3. Okay, so a question like number 4 should not be on the 2020 BC exam because they've cut out the parametrics. So this is a parametric equation. I'm going to do it anyway. X is equal to t squared. Y is equal to t, right? So we need the two derivatives. dx dt is 2t. dy dt is equal to 1. So the arc length for parametrics, it's still over the interval from 0 to 4, square root, but then we take the two derivatives, 2t squared and 1 squared dt. So this is going to give me the integral from 0 to 4, square root of 4t squared plus 1 dt. Then they don't go any further, and that's letter D. So though you will not see something like that on the BC exam this year, you should know how to do one. All right. And problem number 5 is also parametric, so you're not going to see a problem like this, but let's do it anyway. X is cosine cubed t. Y is sine cubed t. Take the two derivatives. So this one comes out as 3 cosine squared t times the negative sine of t. The y comes out as 3 times the sine squared t times the cosine of t. My tendency here is to kind of clean this up a little bit, move that negative out front. I don't think it's going to matter much in this problem, but there we go. So we take the integral. So the interval here is 0 to pi over 2. And we square both of the derivatives. So 3 squared is 9. Alright, we had to take a square root in there, right? So 3 squared is 9. Now we get cosine to the 4th t sine squared t plus 3 squared is 9 sine to the 4th t cosine squared t all dt, and that looks like letter D. Again, parametric problem, won't be on the exam. However, it's worth knowing how to do. Alright, so let's look at number 6. X is a third t cubed. Y is a half t squared. Again, a parametric problem. One that's not likely to be, or it won't be on the BC exam, but we know how to do it. We take the derivative with x respect to t, that's t squared. Take the derivative with y with respect to t, that's t. The length should be the integral from 0 to 1, square root. T squared squared is going to be t to the 4th, plus t squared is going to be t squared, dt, and that's letter C. So some of these that won't be on it are actually kind of quick and easy, but that's what we got. Okay, so problem 7 causes us to reverse engineer. We're told that the length is the integral from 1 to 9 of the square root of 1 plus 9x to the 4th dx. Okay, so that's what we're given. Now, note, that looks like the formula. The integral from a to b square root of 1 plus dy dx squared dx. So this means that dy dx squared is equal to 9x to the 4th, which means that dy dx is equal to, not 9, but 3x squared. Okay, so manipulating that a bit, we get that dy is equal to 3x squared dx. If I take the integral of both sides, I get that y is equal to x cubed plus some constant. Now, they give me an initial value here. They tell me that the initial value is 1/6. So this means that if I put the 6 in for the y and the 1 in for the x, well, let's see. 6 is equal to 1 plus c. C then is 5. So y would have to be x cubed plus 5, which looks like answer B. Okay, so problem number 8 is also a parametric problem, which means it won't show up on the 2020 BC exam, but let's work it out anyway. We have the x is the sine of t cubed, y is equal to e to the 5t, dx dt then should be the cosine of t cubed times 3t squared. I'm going to rewrite that as 3t squared cosine t cubed. Dy dt should be then 5e to the 5t. So the arc length here should be integral from 0 to pi. Those are our bounds. Square root. We square this. We get 9t to the 4th cosine squared t cubed plus, let's see, 5 times 5 is 25, e to the, let's see, e to the 5t squared would be e to the 10t dt, and that looks like C. All right, so again, parametric problem, not going to be on the exam, but so there's some good derivative practice in there, if nothing else. All right, so problem number 9 is back to straightforward one-dimensional case. They're giving us that y is equal to x to the 4th, so dy dx is going to be 4x cubed. The arc length here is simply the integral from 1 to 5 of the square root of 1 plus, and then 4 squared is going to be 16, x cubed squared is x to the 6th dx, and that there is d. So that one's pretty straightforward. Okay, so the last curve here is y is equal to the natural log of x. That means dy dx is equal to 1 over x. So the arc length here is going to be the integral from 1 to 2 square root 1 plus 1 over x squared dx. Simple as pi, and that is letter B. And that is everything on arc length. So remember, the arc length problems in 1 dimension should be on the test. The arc length problems in 2 dimension will not be on the test for 2020 because of the amendments that are being made. I think we're in good shape here. I have made some adjustments in the calendar, trying to pick up some time. So, all right, hope you're all well. And remember, the drop-in sessions are there so that you can get some additional help if you need it.